morning children. Welcome back to your chemistry class. So we had already begun with the isomerism and yesterday we had done structural isomerism. How many structural isomerism did we do yesterday? We had done ionizational structural isomerism, then hydrate, coordination, linkage and coordination position isomerism. Then today we were scheduled to do stereoisomerism, and stereoisomerism is of two types. What are they? Geometrical isomerism and optical isomerism. Now let us understand firstly what is stereoisomerism. When your molecular formula is same, when your structural formula is same, then what is the difference that gives us the stereoisomerism over here? Orientation is different. Orientation of the ligands is different, and since orientation is different, therefore physical properties also are different. Therefore physical properties of the compound is also different. So then in this case we say the compounds, they show stereoisomerism. Clear? Then stereoisomerism is of two types, geometrical isomerism and optical isomerism. So let us begin with the first one, that is geometrical isomerism. Geometrical isomerism. So let us begin with the complex compound with coordination number 4. If a complex compound has coordination number equal to 4, then it will show two kind of structures. What are those two kind of structures when coordination number is 4? It is going to be either square planar, or it will be a tetrahedral structure. What did I say? That if a complex compound has coordination number 4, then it will show two structures. What are those two structures? Square planar or tetrahedral structure. Now firstly understand about tetrahedral structure. In tetrahedral complexes there is no geometrical isomerism found over here. Why so? Because all the bonds at the angle, they are 109 degree 28 prime, and therefore the tetrahedral structures, they do not show geometrical isomerism. I hope this is very clear. I am mentioning it over here. In tetrahedral complexes, no geometrical isomerism is seen because all the bonds, are at the angle of 109 degree 28 prime. That I mean to say that if this is the central metal atom, then you can see the angle that will be formed is of 109 degree 28 prime, Therefore, due to this tetrahedral structure, they are not going to show geometrical isomerism. So this point is very clear. Now we are left with the square planar. Now square planar is going to show you the geometrical isomerism. This was the first point. This is the second point. Square planar complexes show geometrical isomerism. So here I'm going to show you some of the square planar complexes. How do they exhibit geometrical isomerisms? So let us begin with the first one, that is M(A2) B2. Okay, so let us look at the structures formed by this square planar complexes. It is going to show you trans and cis. How? This is your central metal atom AA. See, two ligands of A are there. This will be B and B. So what if I join them all like this? Okay, so this is called as your trans. Why is this called as trans? Because if we see over here, the AA is forming 180°. Therefore, it is a trans, or in other words, we can say the molecules with two atoms and they are opposite to each other. Then they form trans. Okay, and the other one will be like this is the central metal atom. This will be A, this is B, this is B, this is A. So over here what are you seeing? You are seeing both the A's to one side. That is molecules of the two atoms, they are shown, the molecules of the same atoms, they are shown at the same side. Then in that case they exhibit cis, or in other words we can say the A or the same atoms, they form 90°. Then they show cis. This is clear. So one of the examples that we can write over here could be this. What is the name of this? Let us find out the name of this. Diamine, right? Diamine. Then dichloroplatinum. And what is the oxidation state of platinum? If you check, it will come out to be 2. So this is the name of the compound. Let's come to another example where the complexity that I am going to take will be Ma2, B and C. Okay, so over here again it is going to form trans and cis geometrical isomers will be shown over here. So look how it is going to show you. This is A, this is A, this is B, this is C. So AA, that means it forms 180°, or they are opposite to one another, same atom opposite to one another. Therefore, this is what structure formed. This is your trans. Now let us see the cis formation of this complex, square complex. M is here. So this is AA, then it is going to form, when the same atom is to one side, it is going to show you the cis form. Okay, and here it will be B and C. So this is your cis. Let's take an example of this kind of a complexity, like it could be platinum. This is, if A2 is there, I take NH3 whole twice. B is your chlorine and C is your bromine. So what do we name this as? This becomes diamine. Now chloro or bromo? It will be bromo first and then chloro. Okay, so bromido, chlorido, platinum. Now 2. I hope these two complexes are very clear to you. Now coming to the third example, like for example the complexity where you have all the ligands are same, right? Or maybe three ligands are same, then no geometrical isomerism will be formed. So I'm mentioning it over here, all four, or maybe it could be this combination also. So when these combinations are there of the ligands, what combination? If all ligands are same or if three ligands are same, then they do not show geometrical isomerism. No geometrical isomerism shown. I hope till here it's very clear. Coming to the fourth complexity of coordination number 4 of the square planar complex. So it could be M, A, B, C, D. What is this? When all the four ligands are different. In that case, it is going to form three isomers. When all the ligands are different, then it is going to form three isomers. What are they? Let's observe over here. All ligands are different. Okay. So first probability could be M, A, B, C, A, B, C, D. This could be one. So over here we can say A is trans to C. This is not clear. A is trans to C. Then another figure that can be formed could be M. It could be A, B, C, D. This is also possible. So over here A is trans to B. Fine. Another, as I told you, three isomers will be formed. Three isomers are formed when all the ligands are different. Okay. So one I have drawn, two I have drawn. The third one could be M, A, B, C, D. So over here if you see, what have I drawn? A is trans to D. So all three isomers are of trans form. Clear? So let's take an example over here. For example, it could be platinum bromidochlorido NH3 and then pyrimidine. Okay, this could be the example where all your four ligands are different. So this was all about your coordination number 4. Now we are going to discuss about those complexes whose coordination number is 6. Geometrical isomerism with coordination number is 6. Then what kind of a structure do they form? They form an octahedral structure. So if you remember, when coordination number was 4, then it formed square planar or tetrahedral, right? Tetrahedral does not show geometrical isomerism, and square planar I had shown you so many. Now we are coming to those complexes whose coordination number is 6. So what kind of a structure do they show? Octahedral structure. So let us understand what kind of geometrical isomerism is shown by some of the combinations of the ligands, right, in the complexes. So the first one could be MA4B2, where what do we see? 4 ligands are of one kind and 2 ligands are of different kind. means A and B. These two ligands are different. 4 ligands are of same types and 2 ligands are of same type. But A and B, they are different. So what kind of the structure are they going to form? They will form trans and cis. So how? Let us see that. M, this can be A because A ligand is 4, and this could be B. Okay, so what does it show? It shows trans. Why? As BB, they form 180 degree. Okay, so geometrical isomerism of this particular compound, what can that be? It can be formed like this: M, the central metal atom, then this could be B, A, A, A. This can be another form, and here is B and here it is A. So what kind of a structure is this? Form is cis. Why? As BB is now at 90 degree. BB is at 90 degree. Therefore, it forms cis. Let's take an example of this kind. It could be this. Followed? So, what is that? Tetraamine dichlorido cobalt 2. Okay, why 2? Because this becomes 0. This is minus 1 into 2. Cobalt will become plus 2. Let's come to another combination where 3B3. Okay, where 3 ligands are of one kind and 3 ligands are of another kind. In this case, we form Fak isomerism and Merry isomerism. Okay, and they are colored isomers. So let us draw this. This could be B, B, this is A, this could be A. Then here we can see it will form A and B. Okay, so if you look at this, and it forms a Fak isomerism. Okay, is this point clear to you? Then another one. This is A, B, A, A. This will be B, B, and here it is going to show you Merry isomerism, and in this case we will find fine. So these are the two geometrical isomerism when we have 3 ligands of one kind and 3 ligands of another kind. Example could be Cl3NH3 whole thrice. Okay. So what is the name of this? Triamine trichloridochromium 3. Fine. We come to third example of coordination number 6. It could be MAA2B2. Okay, let us look at this combination. So this is also going to form trans or cis. How? Let's see that. M, this could be A, this is B, B. and you will see they form geometrical isomer. And another one could be over here, it could be B, A. Just now I'll show you. This is A, B. Over here, BB is 90 degree. This is your cis form. Okay. Example, it could be cobalt chloride N squared plus. The next example, where complex is having 6 different ligands. Okay. M, this will be A, B, C, D, E, F. Then in this case they will exhibit geometrical isomerism. How many? Theoretical 15 different isomers are possible over here. 15 different isomers are possible over here. Okay, so this was all about your geometrical isomerism. Let us begin with optical isomerism. To understand optical isomerism, there are 2 points that you need to understand. That is, compounds which do not possess any element of symmetry or chirality, they are optically active. Okay, so compounds which do not possess any element of symmetry or chirality. I hope you know what is chirality. It is the property found in a molecule which cannot superimpose on its own mirror image. That is called as chirality. They are optically active. Clear? Second point, the presence of an element of symmetry, it makes a molecule symmetric, and these compounds are optically inactive. Okay, so presence of an element of symmetry makes a molecule symmetric, and these compounds, what are they? Are optically inactive. Fine. So what do we conclude by these 2 points? That if a molecule does not possess any element of symmetry, its mirror image is not superimposable on the molecule itself. This makes the molecule optically active. Clear? Such molecules, they exhibit optical isomerism. Fine. The 2 forms of mirror images, what are they called as? Enantiomers. The 2 forms of mirror images are called what? Enantiomers. Fine. If one rotates the plane polarized light in clockwise direction, then what kind of isomer do they form? They form D form. Okay. So if one rotates the plane polarized light in clockwise direction, then what it is? Then it forms D form, okay, isomer. But if one rotates the plane of plane polarized light in anti-clockwise direction, then what does it form? It forms L form. Fine. Begin with the complexes with coordination number 4. Okay. Now coordination number 4 means which two structures are we going to talk about? We will talk about square planar and we are going to talk about tetrahedral structures. Okay. Now if you remember, tetrahedral structures, they do not show geometrical isomerism. Now we are talking about optical isomerism. Over here, square planar is not going to show optical isomerism. Why? Because all the four ligands, they lie in the same plane. That is, they show no chiral property and therefore no optical isomerism is obtained in square planar. Is this point very clear? Now let us discuss about tetrahedral structure. These compounds, they have asymmetrical tetrahedral carbon atoms and they are generally optically active. And it is expected that these tetrahedral complexes with 4 different ligands might show optical isomerism, but they do not resolve to show either the D or the L forms of complex due to their labile nature. Thus, optical isomerism is not possible in either square planar or in the tetrahedral complexes. Is this point clear? Now next we move to those complexes where coordination number is 6. Okay. So if it is a 6 coordination number, then we are discussing about octahedral structure. Let us talk about those complexes whose coordination number is 6. So over here you should remember that the octahedral complexes containing one or more chiral ligands, they show optical isomer. Okay. So let's see the first complexes like MAA3. Over here we have 3 bidentate ligands and there are no geometrical isomerism shown over here. Because they have the octahedral structure, they are going to form D form and the L form. So how? Let's see that. This is A. Okay, here you can see, this you can see. Fine. And let's see the optical isomerism of this. This when goes to the other side, how will it look? M. This is A. So this portion goes other side. This shows the mirror effect. This comes this side. Okay. So this is your D form and this is your L form. Right? Optically active, forming 2 isomers. Then come to another complexity where we have AA2 B2. This kind of a complex. Here it shows 3 isomers. What are those 3 isomers? M. This is A, B2, B and B. Okay. So if you are going to observe, this is forming your trans because this is at 180 degree. Okay, optically active. What is it going to show us? This comes this side and this goes the other side. The structure remains the same. So no optical isomerism will be formed if we take this trans form. Okay. No optical isomer is formed with the trans. Whereas if you look at the cis, I'll draw it for you over here. M, this is B, A, B, A. Okay. If you look at this figure which forms cis, then it is going to show optical isomerism. This is D form. Okay. And what is it going to form? It should form L form. So let's observe whether it forms L form or not. This is, if this part comes this side, it becomes A, B, A, this is B, this is A, this goes the other side, right? And this comes the other side. So it forms the L form. So I hope you have understood how many? 1, 2, 3. As I said, 3 isomers are formed here. 3 isomers will be formed over here. Clear? Now, the last part of it, that is all those octahedral complexes of this kind. Okay, M, A2, B2, C2. Okay, then M, A2, B2, CD, or maybe M, A2, B, C, D, E, and even M, A, B, C, D, E, F. They all do not possess optical isomerism. Is that clear? So with this, we finish off with the isomerism in the coordination compounds. Tomorrow, I shall begin with the valence bond theory. Thank you.